Now we talk about chemical bonding and Lewis theory. So write the Lewis theory or Lewis structure for phosphorus. So the idea with Lewis is he thought that electrons were like, well, atoms are like boxes and electrons are like the corners of the boxes. So of course he was right about the number 8, wrong about the reason, but it works pretty well. It's a pretty powerful theory. Start off with phosphorus. Phosphorus has 5 valence electrons, so we put 4 dots around it, and then we group the second one there on the end. So that's where the 5th dot goes. Write the Lewis structure for the compound magnesium oxide. So magnesium has 2 valence electrons and oxygen has 6, and there are their Lewis structures. And magnesium is a metal and oxygen is a non-metal, so these tend to form ionic compounds. So magnesium is going to give 2 electrons to oxygen to give its octet, and then the octet shows the full octet with the whole. All you see, all these are paired around the atom. And we put the +2 charge on magnesium, and then the brackets with a -2 charge around the oxide there to show the ion's charge. So similar, predict the formula for calcium chloride. So calcium has 2 valence electrons, chlorine has 7, and so that means calcium tends to lose 2 electrons and chlorine tends to gain 1. And because of that, you need to have 2 chlorines to absorb the 2 electrons from calcium. So calcium chloride tends to have a 1 to 2 molar ratio between calcium and chlorine in that. So write the Lewis structure for carbon dioxide. So first thing we do is write the skeletal structure and put carbon in the middle there, and then the total number of electrons. So there's 6 for oxygen, there are 2 of them, so 6 times 2 is 12, plus 4 for carbon, so that's 16 electrons. First thing we do is we put a single bond between them, so we've placed 4 electrons. So 4 electrons, and now we put the remaining electrons around it to give octets to the outer atoms. So oxygen now at this point in time has an octet, and carbon only has 4 electrons. Carbon wants to have 8 electrons, so you're gonna add double bonds from each of the oxygens then to ensure that carbon does in fact have a complete octet. Now each atom has an octet, so this is a proper Lewis structure. So this is good. So write the Lewis structure for carbon tetrachloride. Similar one here, put carbon in the middle, and then we sum the valence electrons. So 4 for carbon, and then there's 7 for chlorine, but there's 4 chlorine, so we have 32 electrons. So we put octets, so we put single bonds, and then we put octets around the outside. And if you look here then, carbon has an octet, and each of the chlorines have an octet. So we're actually done. We're done. And we don't need a double or triple bond. But you might start to notice something. So hydrogen and the halogens tend to bond with 1. Oxygen tends to bond with 2. Oxygen and sulfur tend to bond with 2. Nitrogen and phosphorus tend to bond with 3. And carbon tends to bond with 4. So, I mean, like as far as like the number of bonds. That's not true for everything, so be careful with that. But that is generally how most molecules form. You can have expanded octets, for instance, in compounds that are in the 3rd period and below in the periodic table. And sometimes there's odd number of electrons. Sometimes things don't bond to an octet like boron or aluminum. So but that general rule holds pretty well. So let's write the Lewis structure for a polyatomic ion like ammonium. So we're going to do the same thing with skeletal structure. Now we sum up electrons, but now what we do is we subtract 1 for the +1 charge. So you would think we have 9 electrons to work with, but we only have 8 because of that. So we're going to put single bonds there to each of the hydrogens. And notice that we placed all 8 electrons. And now look at that fancy stuff. We have nitrogen has an octet. Nitrogen has an octet. Hydrogen has a duet. So we're done, except we have to put a bracket around it and put a positive charge on it. So that's that one for that. So let's write a resonance structure. So the nitrate anion. So similar, put nitrogen in the middle, surround the oxygens for the skeletal structure. Now we sum up the electrons. So 5 for nitrogen, 3 times 6 for the 3 oxygens, and then plus 1 for the -1 charge. Remember, negative means an extra electron. We have 24 electrons. So now we give a single bond to each of the nitrogens and oxygens, and then we fill up the octet. So we've used all 24. Now there's a problem with this because although the oxygens have octet, nitrogen only has 6. So nitrogen is going to have a double bond. So we're going to go ahead and put a double bond there for one of the oxygens, and surrounded by brackets, and put the negative charge. Now the problem with this is, though, that there are you can have equivalent of 3 other structures. So because of that, this is known as a resonance structure, which means that they can go back and forth between them. So then you show the resonance by showing these double-edged arrows here. And so that would be the most proper way to do it. And if you wonder, is this what happens in real life? Well, Lewis theory, it's a good theory, but it's not exact. The better theory is quantum mechanics and molecular orbital theory. And what happens is that when a group of atoms, positive charges with the nuclei and their electrons, when they come together, their atomic orbitals can change into molecular orbitals, and then those molecular orbitals are then filled by the same rules, with the Aufbau principle, with the Hund's rule and all that kind of stuff, building up low energy to high energy, and those electrons are populated into those orbitals. So and the electron, it doesn't care. It's not like it's got a loyalty to a certain atom. It's fine to be shared between atoms, so it's fine with that. And that's really what happens. But Lewis theory, and you're still learning chemistry, and this is a very powerful theory. Even though it's fundamentally wrong, it's still a very powerful theory, so we still teach it. So let's predict the geometry using valence shell electron repulsion theory. So VSEPR, sometimes called VESPR, but I know it's VSEPR, valence shell electron pair repulsion. So draw loose. So start with the molecular geometry of phosphorus trichloride. So we draw the structure as before. So draw the structure. Now let's look at the phosphorus trichloride. It has 4 things. So the phosphorus atom has 4 things around it. It has 3 bonding groups and a lone pair. So the 3 bonding groups and lone pair, and then we look to see the geometry. And so 4 things, 3 bonding groups, lone pair, and that's the second line from the bottom. So that means that the electron geometry is tetrahedral, and the molecular geometry is trigonal or trigonal, whatever you want to say, trigonal pyramidal. So it is a trigonal pyramidal structure. And so then that's that. So what type of bonding is formed between each of these? Pure covalent, polar covalent, or ionic. So if you look here, look at the electronegativity difference. I don't have it memorized, but I know it's going to be a lot. So strontium and fluorine, it's going to be a big electronic difference. Oh, it's written right there. That's nice. There's a 3 by Pauline's electronegativity. It's greater than 2. So then we can classify this as ionic. Nitrogen and chlorine, they're about the same electronegativity. By this book, you can call it pure covalent. I would disagree personally, but I'm a physical chemist, and for advanced classes, you might consider this to be polar covalent. But for this class, and if you want to be an organic chemist, you can consider that to be covalent. But sure, for this class, that's covalent. And nitrogen and oxygen, there's about a half a electronegativity difference between that. And so because of that, that's a polar covalent bond. So here are the things here for that. If you must know the difference, and there is a slight difference, and so there is going to be a slightly polar covalent bond between chlorine and nitrogen. It's not very significant, but it's some. So and then you can see there for nitrogen and oxygen. Here it shows you the Pauline's electronegativity, and where the numbers come from. And here are the different bond types. So, okay. And is ammonia polar? So first thing we do is write the Lewis structure, and we get Lewis structure, and it is pyramidal. This is a pyramidal structure, and if you look at the bonds, so because of the bonds here, it's going to be polar. You're going to have a net flow of electron density towards the nitrogen. There's going to be a negative end at the top and a positive end on the bottom, assuming nitrogen is the top of the pyramid. So this molecule is in fact polar. And some hints here. So if any, all bent and all pyramidal molecules are polar, no exceptions, even if they're the same atom. So ozone, 3 oxygens. So that's a bent molecule. And that's a polar molecule. So no exceptions to bent and pyramids being polar. If things are linear, planar, or tetrahedral, if all the groups are the same, then it's going to be nonpolar. If any one of those groups are different, then it's going to be polar. There are a couple exceptions to that, though. Then you can have something called cis-trans isomerism. So depending on the groups for things, you'll have to learn about the cis and trans. Another shortcut is if it's a hydrocarbon, it's nonpolar. So there's a couple things there. So hydrocarbon, of course, means all hydrogen and carbon for the molecules. So a couple rules there. We don't talk too much about cis and trans in this class. So cis and trans for planar can complicate things, but that's a general. It depends on the different group and where the groups are. So hopefully I'm making life easier by talking about that, generally speaking. So although much of it is beyond this class. So. And we are done. Thank you for listening.